Hello everyone and welcome to the Control Engineering and Control Theory tutorials. In this tutorial we will cover the final value theorem. We will formulate the theorem, then we will provide several examples to illustrate the applications of this theorem, and then we will explain how to correctly and incorrectly use this theorem. Namely, we have noticed that in practice a number of engineers as well as students sometimes incorrectly use the final value theorem. And consequently, we will give several examples where you cannot actually use the final value theorem. But before we start with explanations, we need to explain the main motivation for studying and learning the final value theorem. Namely, every student studying control engineering or every engineer using the basic principles of control theory to design controllers need to perfectly understand the final value theorem. This is mainly because the final value theorem is used to analyze the steady state control errors as well as to minimize, or better to say to optimize, the control performance. Also, it has a number of applications in control theory. I cannot imagine myself as a control engineer without the knowledge of the final value theorem. So here's the problem. We are given a Laplace transform, capital Y of S, of a time domain signal, lowercase y of t, where t is time. And then, someone asks us the following question. What is the steady state value of y of t? That is, what is the steady state value of the time domain signal? Or, what is y at infinity? Again, someone only gives you the Laplace transform, capital Y of S, without actually giving you the time domain signal y of t, and this person asks you, what is y at infinity? The final value theorem has two equivalent statements. Here is the first statement. Let lowercase y of t be a time domain signal and let capital Y of S be its Laplace transform. Then assume that Laplace transform y of S has all the poles in the open left half of the complex S-plane and at most one pole at the origin. Then the limit value when time goes to infinity of the time domain signal y of t is actually the limit value when s goes to 0 of s multiplying the Laplace transform capital Y of S. Over here again, capital Y of S is the Laplace transform of the time domain signal lowercase y of t. Here is the second statement of the final value theorem. Let lowercase y of t be a time domain signal and let uppercase or capital Y of S be its Laplace transform. Then assume that the poles of s multiplying y of s, that is s multiplying the Laplace transform y of s, are in the open left half of the complex S-plane. Then we have the limit value when t goes to infinity of the time domain signal y of t is actually equal to the limit value when s goes to 0, s multiplying the Laplace transform y of s. And that's it. So what's the difference between the first and the second statement? Well, the second statement is less complex. This is mainly because over here it's required that the poles of s multiplying capital Y of S are in the open left half of the complex S-plane. However, this second statement is actually equivalent to the first statement, and here's the reason. By multiplying actually y of s by s, we are actually eliminating a possible pole in 0. So if we just multiply this by this, all the poles should be strictly in the left half of the complex plane, and then we can apply the final value theorem. And that's it. Simple as that. Next, let us graphically explain the final value theorem. So what we are given? We are only given capital Y of S. And we are not given the time domain signal. That is, y of t is not given to us. Okay, We don't have information about y of t, we only have information about y of s. Then, without actually computing the inverse Laplace transform and computing the time domain signal, we don't go this path. We actually want to conclude what is y at infinity. That is, what is the steady state of the time domain signal. That is, to summarize, we are given only the Laplace transform or a transfer function or something similar, and we want to see the steady state value of the corresponding signal in the time domain. To apply this theorem, the poles of y of s have to be located over here. Let me illustrate the locations. Here's my complex plane. This is the real part of S. And this axis will denote the imaginary part of S. All the poles of y of s, I will put y of s over here, have to be strictly in the open left half of the complex plane. That is, they should be over here, and at most, we can allow or tolerate for a single pole at 0. That is, only single pole at 0 is allowed. Only a single pole, and all the poles should be over here. We cannot also allow poles on the imaginary axis, so forget about it. So all the poles should be strictly in the left half of the complex plane. If that's the case, then you can apply the final value theorem. Okay, let's start with examples. We are given the Laplace transform over here, and we want to compute the steady state value of the time domain signal. That is, we want to compute in the time domain y of infinity. So how to do that? Well, first of all, we have to make sure that we can actually apply the final value theorem. So what are the conditions for the applications? Number one, all the poles of capital Y of s should be strictly in the open left half of the complex plane, and we can allow for a single pole at 0. Is that the case? Well, first of all, we need to verify the poles. So what are the poles of this system? The poles are the zeros of the polynomial in the denominator. Here's the polynomial in the denominator. And let's compute zeros. We have 1 0 actually at 0. And we have 2 additional zeros. I will denote them by S2, 3. By applying the quadratic formula, we can compute these zeros. They are -7 plus minus square root of, let's see, b squared is 49 minus 4ac. A is 1 and c is 3, so it's 4 multiplying 3 divided by 2. From here we can see that S2, 3 is -7 plus minus square root of, let's see, we have 49 minus 12 divided by 2. Consequently, S2, 3 are -7 plus minus, let's see what do we have over here. 49 minus 12 is actually 37. And this should be divided by 2. By substituting the values in the calculator, we can see that S2, 3 are actually -7 plus minus 6.083 divided by 2. And we can see that both S2 and 3 are on the real axis, and both of them are actually negative. This means that S2 and 3 are strictly in the left half of the complex plane, and furthermore we have a single pole at 0. This means that we can apply the final value theorem. Okay, so let's apply the final value theorem. We can write limit value when t goes to infinity, y of t, and this is actually equal to y at infinity, is actually equal to limit value when s goes to 0, s multiplying y of s. In our case, y of s is given over here. So let's substitute the values. So we have limit value when s goes to 0, s multiplying s plus 5. Let me nicely write it. Divided by s multiplying s squared plus 7s plus 3. We can see that we can cancel s and s, so we are left with limit value when s goes to 0 of s plus 5 over s squared plus 7s plus 3. And since this function is continuous, we can actually substitute s is equal to 0, and we can obtain that this limit value is 5 over 3. And that's it. This is the steady state value of the time domain signal y of t. Now, let's analyze what we did. We never computed the inverse Laplace transform of this transfer function. However, we are able to conclude the steady state value in the time domain, and it is 5 over 3. And that's it. Here's the second example that illustrates the application of the final value theorem. The example goes like this. Given a transfer function, w of s, given over here, compute a steady state control error for an input signal equal to a unit step signal. Let's solve this example. Well, to solve this example, first you have to remember and to recall what is a transfer function. The transfer function relates the outputs to inputs. In the complex Laplace domain, y of s, that is the output, will be the transfer function w of s multiplying u of s, where u of s is the Laplace transform of the applied control signal. If we read carefully the problem, you can see that it is assumed that the input signal is a unit step signal. In the time domain, the unit step signal is usually denoted like this: 1 multiplying h of t, where h of t is the so-called Heaviside function. Heaviside function. Now, the Laplace transform of the Heaviside function is, let's write it like this, Laplace transform of u of t is actually 1 over s. And this is our u of s. Consequently, our output will be y of s is w of s multiplying 1 over s. The next thing that you need to write down is the definition of the control error. In the time domain, the control error is e of t, input signal. In our case, it's a simple 1 multiplying h of t. Input signal is also reference signal, minus y of t, where y of t is the time domain output. Now, if we apply the Laplace transform to this equation, we will obtain that capital E of s is equal to Laplace transform of 1 multiplying h of t is obviously 1 over s, and we will have minus y of s. From this equation over here, we can substitute y of s as w of s multiplying 1 over s. Consequently, we will have over here 1 over s, let me write it nicely, minus w of s multiplying 1 over s. And this term over here can be factored like this: 1 over s multiplying 1 minus w of s. So let's write our E of s once more over here. E of s is 1 over s multiplying 1 minus w of s. Next, we can substitute our transfer function. So we will have 1 over s, and over here we will have 1 minus 3s plus 1 over s squared plus 3s plus 2. Next we have 1 over s multiplying. In the denominator we will have s squared plus 3s plus 2, and in the numerator we will have s squared plus 3s plus 2 minus 3s and minus 1. And this finally becomes, let's write it over here, E of s is 1 over s multiplying, let's see what we have over here. In the denominator we have s squared plus 3s plus 2, and in the numerator we will have s squared. 3 and 3s can be cancelled. Plus 2 minus 1 is simply plus 1. And that's it. The next question is, can we apply the final value theorem to this example? To investigate that, we need to compute the poles. So what are the poles of this function? The poles are the zero of this polynomial in the denominator. The polynomial is s multiplying s squared plus 3s plus 2. And this should be equal to 0. Obviously, the first pole is s1 is equal to 0. And we have two additional poles. s2, 3 is, let's apply a formula for zeros of a quadratic equation. So they are minus 3 plus minus, let's see. Over here we will have 9 minus 4ac, that is 4 multiplying 1 multiplying 2, divided by 2. So s2, 3 becomes minus 3 plus minus, let's see what do we have over here. We have 9 minus 8 divided by 2. Consequently, s2, 3 is minus 3 plus minus 1 divided by 2. Consequently, s2 is minus 3 minus 1 divided by 2, that's minus 2, and s1 is minus 3 plus 1 becomes minus 2 divided by 2 becomes minus 1. So here are the poles. They are 0, minus 2, and minus 1, and we can observe that the main conditions for applying the final value theorem are satisfied. So we can write E in the time domain at infinity is equal to the limit value when time goes to infinity, E of t, and this is equal to the limit value when s goes to 0, s multiplying capital E of s. Consequently, we will have that E at infinity, that is the steady state of the error, steady state value of the error, is limit value when s goes to 0, s multiplying this whole thing over here, that is the s multiplying 1 over s multiplying s squared plus 1 over s squared plus 3s plus 2. And furthermore, we will have the limit value when s goes to 0. Let me nicely write this. S goes to 0. S and s can be cancelled here, so we simply have s squared plus 1 over s squared plus 3s plus 2, and this becomes 1 over 2. That is, this becomes 0.5. And that's it. This is the solution of our problem. And finally, let's explain how to incorrectly use the final value theorem. Let us assume that we are a student or an engineer and that we forgot the complete statement of the final value theorem and that we just remember the formula involving the limit values. Now, we forgot the main assumptions on the locations of the poles of our y of s, and we simply apply the formula. Let's do that. Here's the problem. Compute the steady state value of y of t if capital Y of s is 2 over s multiplying s squared minus 5s plus 6. And let's just blindly apply the formula. So the formula states that y at infinity is equal to limit value when t goes to infinity y of t, and this becomes in the complex Laplace domain limit value when s goes to 0, s multiplying y of s. And let's substitute the value. Here we have the limit value when s goes to 0, s multiplying, let's write 2 over s squared minus 5s plus 6. S and s can be cancelled, and finally we obtain that y at infinity is actually limit value when s goes to 0, 2 over s squared minus 5s plus 6. And let's compute this limit. We substitute simply s for 0 over here, and we obtain that this is 2 over 6, and this is actually 1 over 3. Okay, so we obtain the result, 1 over 3, and we design our control system, and when we implement it in practice, everything explodes. So what is the issue over here? Well, the issue over here is that if we would directly compute the inverse Laplace transform over here, that is of this expression, we will see that infinity, the signal y of t goes to infinity. Why is that? Well, the reason over here is that you will have a pole that is strictly in the right half of the complex plane, and consequently the time response will go to infinity. We can show that by expanding this function using partial fraction expansion. To show that this function will actually go to infinity in time domain, let's compute the partial fraction expansion. To compute the partial fraction expansion, first we need to determine the poles of this system. So what are the poles? The poles are the zeros of this polynomial in the denominator. That is, the poles are the zeros of this polynomial, s squared minus 5s plus 6, and this is equal to 0. So what are the poles? First pole is s1 is equal to 0, and the second pole, or in the third pole, are the zeros of this quadratic equation. By applying the quadratic formula, we can obtain that s2 or 3 are actually 5 plus minus, let's see what do we have over here. We have a square root of 25 minus 4ac, that is minus 4 multiplying 6 divided by 2. So we have that s2, 3 are actually 5 plus minus square root of 25 minus 24 divided by 2. So what do we have over here? We have s2, 3 becomes 5 plus minus 1 divided by 2. Consequently, we have that s2 is 5 minus 1 divided by 2, that's 4, divided by 2, that's 2, and s3 is 5 plus 1 divided by 2, that's actually 3. Okay, now that we know poles, we can use the partial fraction expansion. Y of s becomes a over s plus b over this pole over here. So we have s, and then we have minus 2 over here, plus c over s minus 3. Okay, over here, we need to compute the constants a, b, and c. Let's first compute the constant a. The constant a is determined as y of s multiplying s evaluated at s equal to 0. Now, by substituting the values over here, that is, by substituting ys from here over here, we will obtain that this is actually equal to 2 over s squared minus 5s plus 6, and this has to be evaluated at s is equal to 0. And this becomes, this is 0, 2 over 6, and that's actually 1 over 3. Okay, how about b? Well, b is computed in a similar manner. We have y of s multiplying s minus 2 evaluated at the pole at s equals to 2. So let's substitute the values and let's see what do we have. This polynomial over here can be factored as s minus 2 multiplying s minus 3. And if we multiply everything by s minus 2, we will simply left with 2 over s multiplying s minus 3. And this should be evaluated at s is equal to 2. And this becomes 2 over 2 multiplying 2 minus 3 becomes minus 1. And this becomes minus 1. And finally, the c constant is determined in a similar manner. It's determined as y of s multiplying s minus 3 evaluated at s equals to 3. Again, we can factor this polynomial as s minus 2 multiplying s minus 3, and if we multiply everything by s minus 3, we will obtain 2 over s multiplying s minus 2 evaluated at s is equal to 3. So let's see what do we have over here. We have 2 divided by 3 multiplying 1, and we have 2 over 3. And consequently, if we substitute the values, we obtain a is 1 over 3, that is 1 over 3 multiplying 1 over s. Then we have plus, let's see what do we have over here, minus 1 for b multiplying 1 over s minus 2, and over here we will have plus 2 over 3 multiplying 1 over, let's see what do we have, we have s minus 3. Now, y of t is simply the inverse Laplace transform of y of s, and consequently y of t becomes the inverse Laplace transform of 1 over 3 multiplying 1 over s is simply 1 over 3 multiplying the unit step function or the Heaviside function. Then we have minus the inverse Laplace transform of 1 over s minus 2 is simply minus e to the power 2t, and over here we will have the inverse Laplace transform of this term, and this is simply plus 2 over 3 multiplying e to the power 3t. And over here we need to add the Heaviside functions, and over here Heaviside function. However, I will ignore that for the time being. So if we see the exact value of y at infinity, we can see that if we let this term to go to infinity, we can see that this term will always be higher than these two other terms, and this will go to infinity. However, our original conclusion from the final value theorem is that y infinity is actually final value, and this is actually the direct consequence of the inappropriate application of the final value theorem. Okay, that's all for today.